Alright friends, so now we're gonna start talking about how to optimize the performance of your database and queries. And one of the most important techniques is to use indexes. So in this video you can have like an introduction about what are indexes. Two very important types of indexing. We have the clustered index and the non-clustered index. And we're gonna learn as well what are the main differences between them and when to use which one. And of course we're gonna practice in SQL on how to create those indexes. So let's go. Hey friends, if you are new here, welcome. My name is Bara and I lead data projects in big companies like Mercedes-Benz, and I'm here to share my knowledge and best practices about data in high quality videos in this YouTube channel. So if you don't want to miss anything, make sure to subscribe. Now let's go back to the video. So what is an index? An index is a data structure that provides a quick access to the rows to improve the speed of your queries. So an index is like a guide for your database in order to speed up the process of searching for data, especially if you have like big tables. So now in order to understand what are indexes, imagine you have a huge book and you want to find a specific topic or a chapter. Instead of flipping each single page in order to find the topic that you are searching for, you would use the index at the back of the book in order to jump straight to the right page. And that's exactly what index does, but for your data. Another analogy that I use in order to understand indexes is, think about the indexes as a big hotel. Now let's say that in the hotel we don't have any guide and you would like to find the room number, let's say 501. Now what you're gonna do, you're gonna go and search for your room floor by floor and checking each room until you find your room. But instead of that, thankfully, hotels have a numbering system and you can ask for a map from the reception in order to understand in which building, in which floor you can find your room. So by just following the map and maybe some signs, it's gonna be very quickly to locate and find your room in such a big hotel. And that's exactly what each database needs. It needs an index in order to help the database finding and locating the right data without having to scan everything. And now let's say that you ask me, you know what, I have this big table and I would like to speed up the queries using indexes. And my first question gonna be, what are you exactly doing with this table? Are you using this table to search for a text, or are you doing like complex analysis with this table? And the reason why I'm asking this is that we have different indexes in databases for different purposes. So now let's have a quick look to the different types of indexes that we have in database. I divide the indexes in databases into three categories. The first one is by the structure, how the database is organizing and referencing the data. And here we have two types, the clustered index and the non-clustered index. Those are very important to understand. Now we have another category for the indexes. We can divide them by the storage. And in this category, we are talking about how the data is stored physically in the database. So we have two types. We have the row store index and the column store index. And the third type is the functions. And here we have two types. We have the unique index and the filtered index. Now each index type has its own strengths, but as well there is always a trade-off. Some might improve the read performance, the other one might improve the insert and update operations. So it's all about choosing the right type of index for the job. So now what we're gonna do, we're gonna go and deep dive into each of those types in order to understand how they work and how we can create them. And we will start with the first category, the structure. We have the clustered index and the non-clustered index. Now before we dive into how the indexes works in databases, let's understand first what happens to the database tables if you don't use any index. When you create a new table in your database, like for example the customers table, where you have let's say 20 customers inside this table, what you're gonna see at the client side is like spreadsheets, like a table with rows and columns. But behind the scenes, the database stores it a bit differently. It's gonna store the data in a data file on the disk, and inside this file, the data can be stored inside blocks called pages. So it's not like rows and columns, data are stored inside data files, and inside the data files we have pages. So what is a page? A page is the unit of data storage in a database, and it is a fixed size of 8 kilobytes where the SQL database can store anything inside it. It can store inside it the rows of your tables or columns, metadata, indexes, and every time you are interacting with your data, the SQL is reading and writing to those pages. So as you can see, the SQL is not storing the data inside like rows and columns. So if you are running a query, the SQL is not like selecting a specific column. It always fetch a data page in order to read the rows inside this page. And the main two tabs that we're gonna learn is the data page and the index page. So how the data page looks like? It is divided into multiple sections. The first section is the page header, where the database is gonna store key informations about the metadata, like the page ID, and it has the following format. It starts with the file ID, like 1, and then we have a unique number for each page. So for example, 150. So the page header is a fixed size of 96 bytes. Now to the next section, we're gonna have a variable size. This is where your data row is gonna be stored. So your actual data and rows is gonna be stored in this section, and the SQL gonna try and fits as many rows as it can in one single page. And this of course depends on the size of each row. So if you have like a large table where the rows are really big, so SQL can fit only few rows in one single page. And now moving on to the last section in the data page, we have the offset array. This is like a quick index for the rows stored inside this page. It keeps track of where each row begins so that the SQL can easily locate a specific row without having SQL like scanning the entire page in order to find a row. So this is the structure of the data page, and this is exactly how the SQL stores data inside the databases. So now back to our example where we have the customers table and 20 rows. So let's see how SQL gonna be creating those pages. Now if you are not using any index in this table, so now what can happen? SQL gonna insert the data inside those pages as you are inserting the data inside the customers. So maybe first you are inserting the customers like 12, 5, 15, 6, 7, and SQL gonna insert it to the data pages exactly like that. So that means SQL is just inserting the data as you insert it to the table. So let's say each data page is like fitting only 5 rows. So after we insert 5 customers, SQL gonna go and create another data page for the next rows. So in the next page, the SQL gonna insert the next 5 customers, and once it's full, it's gonna create another data page in order to start adding the next customer until we have like, for example, 4 pages for the 20 customers. So now if you check the customers inside those 4 pages, you see that they are not sorted at all. And that's because in this scenario, we are not using any index. So we call this structure as a heap structure. So a heap table is a table without a clustered index. That means the rows are stored randomly without any particular order. This is not really bad because it's gonna be very quick to insert data inside this table. But of course, finding something from this table gonna be very slow. So this is the first trade-off. You have a very fast writes but very bad reads. Think about it like you are throwing all your papers in a drawer without organizing them. So you can toss things very quickly in this drawer, but if you want to search for a specific paper later, it's gonna be a very long process until you find it because nothing's in order. So now let's see how the SQL gonna handle if you read something from this table. Let's say that you are searching for the customer with the ID 14. So now SQL has totally no idea where to find this customer. So SQL gonna start fetching each data page and start scanning each row. So it's gonna start with the first data page and start scanning. Well, SQL will not find 14 here. So SQL gonna go to the next page and start scanning as well, searching for the ID 14, and nothing gonna be found. The same thing for the third page. As well, SQL will not find 14, so SQL gonna go to the last data page, and there, after scanning 4 rows in this data page, finally SQL gonna find the customer number 14, and it's gonna return it for the client. So as you can see, in order to find one customer, SQL did read 4 different pages and scanned like 19 rows in order to find the customer. And this process, we call it full table scan. So the full table scans means SQL is scanning the entire table page by page and row by row in order to find specific row. And of course, for this table, maybe it's not a big deal, but if you have like a big table where you have like hundreds of thousands or maybe millions of rows, searching through the heap structure gonna be very painful and slow in order to locate one row. And here exactly why we need indexes in SQL databases. So let's understand the first type of indexes, the clustered index. Alright, so now let's understand what can happen if you create clustered index in your table. So say you created clustered index on the ID column of the customers. So the first thing that's gonna happen, SQL gonna physically sort all the data based on the column ID. So the rows gonna rearranged in each data page from the lowest to the highest. So on the first page, we're gonna have the first customer, ID number 1, then 2, 3, 4, 5, until we reach in the last page, the last customer number 20. So as you can see, the first page has the lowest value and the last page has the highest value. So that's not all. The next step is that SQL gonna go and start structuring and building the B tree. So what is a B tree? A B tree, short for balance tree, it is hierarchical structure that stores the data as a tree upside down. It starts with the root node, and then it keeps branching out until we reach eventually the leaves. Between the leaf nodes and the root node, we call this section the intermediate nodes. So it could be like one level or multiple levels between the root and the leaves. And once SQL constructs the B tree, it's going to be very easy for SQL to navigate through the B tree in order to find specific information. So let's see how SQL is building the B tree for the clustered index. Now, very important to understand that the leaf nodes at the B tree for the clustered index contain the actual data, the data pages. So all your nice sorted data pages and your data is stored at the leaf level. Then after that, SQL gonna start building the intermediate nodes. And here the database gonna use different type of pages. We have the index page. So in the index page, we cannot find the actual data, the entire rows, but instead the index page stores a key value that contain a pointer to another index page or to a data page. So for example, we have here the value 1, the key, and then the value gonna be the ID of the data page. So here we don't have like the whole row about the data, we have here only a pointer to another data page. So here we are telling SQL, if you are searching for IDs between 1 and 5, you can locate it at the data page ID 100. And then we can store in this index page another pointer where we can tell SQL, if you are searching between 6 and 10, then you can locate it at the second data page. So this is the structure of the index page. It contains only pointers to another page. And the same thing for the second two pages. The SQL gonna create another index page where it's gonna says, if you are searching for IDs between 11 and 15, you can find it at the third page, 100.102. And for the last group between 16 and 20, we have another pointer to the last page, to the page number 100.103. So as you can see inside those index pages, we have like a pointer for each group of IDs, for each cluster. So for the group of customers between 1 and 5, we have one pointer. And for the second group between 6 and 10, we have another pointer. So that means we don't have here a pointer for each row. We have a pointer for each group, for each cluster. That's why we call it a clustered index. And now once SQL is done building the intermediate nodes, SQL gonna go and build the last node, the root node, where it says if you are searching for customers between 1 and 10, then go to the index page with the ID 100.200. So that means the root node here is pointing to another index page, not directly to the data page. And the same thing, we need another pointer for the second index page. So the customers between 11 and 20 go to the index page with the ID 100.201. And this is exactly what can happen if you create a clustered index in SQL. First, it's gonna go and physically sort all your data in the data pages. So if it's from the first time sorted randomly, SQL has to arrange everything and sort the data from the scratch. And then it's gonna go and build this structure where you have in the root node an index page, in the intermediate nodes the index pages, but at the leaf level, at the leaves, we have the actual data, the data pages. So now let's see what's gonna happen if you query the table where you search for the ID number 14. So it's gonna check which pointer to use. Since 14 is in the group between 11 and 20, it's gonna go and use the second pointer to the index page with the ID 1.201. And here the SQL gonna open this index page and check the pointers. So since 14 is between 11 and 15, it's gonna go and use the pointer to the data page 1.102. And with that, SQL located the correct data page, the third page, and now SQL gonna open this data page and find the customer ID number 14. So as you can see, it was very fast for SQL to locate the correct data page. With only 3 jumps from the root node to the intermediate node, the SQL were able to find fast the correct data page. And here SQL needs only to read one data page instead of reading, as we saw in the heap structure, 4 different data pages. And of course you might say, but still here we are reading like 3 pages. Well, reading an index page is very fast compared to the data page, because reading a data page is always slower than reading an index page. So as you can see, this B-tree structure, the clustered index structure, did help the SQL and the database to locate the right data in the right data page without having unnecessary read operations on different databases. And this is exactly how the clustered index works in the SQL database. Alright, so now we're gonna move to the second type and we're gonna understand how exactly SQL build and create the non-clustered index. So let's go. So now we are back to the heap structure where our table don't have any index and our data are stored randomly inside the data pages. And now if you go and create a non-clustered index on the customer ID, what's gonna happen? And here the big difference is that SQL will not touch or change anything on the physical actual data on the data pages. So the data page is gonna stay as it is and nothing gonna be changed. And the SQL start immediately building the B structure. So it's gonna start immediately building an index page. And this index page is a little bit different than the one that we have learned previously. So since it's this index page, it's gonna store pointers. But this time SQL gonna store in the key the customer ID. So one is the customer ID, and now the value, the pointer, it will not be the data page ID. We will be more specific, so we're gonna have like an address where exactly the row is stored. So it's gonna start with the file ID, the page number, because the customer ID 1 is stored in the page 1.102, but SQL gonna go add as well the offset number of the row, where exactly in the page we can find this ID, and the whole thing we can call it an RID, the row identifier. So now let's see quickly how the index page is pointing exactly to the row inside the data page. So the first part of the row identifier is mapping to the data page ID, and then from the 96 it's gonna take us to the offset, and that's exactly the location of the row number 1. So 96 is the part where we're gonna start finding the row number 1, and that's gonna take us exactly to the place where we can read the information about the row ID number 1. So this is how the index page is locating the exact place of the rows. So SQL can go and continue and assign for each customer ID a pointer to the exact location. So as you can see now in the index page, we don't have like a pointer for each group of customers like we have learned in the clustered index. We have now a pointer for each ID, and this type of index page we call it row locator page. So now SQL gonna go and continue and map a pointer for each customer ID that we have inside our table. So we will have multiple index pages pointing to our data page. So as you can see, we have a lot of pointers, and the data inside the index page is of course sorted, but inside the data pages it left as it is. And now those index pages that has the row identifier gonna be stored at the leaf level of the B tree. So at the leaf level, we don't have the actual data, the data pages. We have index pages where we have pointers then to the actual data. And then SQL gonna go and start building the intermediate nodes. It's exactly like the clustered index where it's gonna point to another index page. So between 1 and 5 customers, it's going to be in the index page number 200. So the next step is going to go and build the intermediate nodes. It's going to be exactly like the clustered index. Nothing going to be changed. It's like the same structure. So it is an index page pointing to another index page, but this time for a group of customers. And then we're going to have as well the root node. So again, we call this structure as a B-tree structure where they point to another data pages, but the data pages are not part of the B-tree. So now let's say if you are searching for the customer ID number 14, what's gonna happen is SQL gonna start again from the root node, and then it's gonna find the pointer to the intermediate node and then jump to the next step to the intermediate node, and then it's gonna find the pointer to the index page between 11 and 15, and then SQL gonna go and scan this index page and find, okay, for the customer ID number 14 we have the following address. So it's gonna go and locate the exact data page and as well the exact place of the row. So it can go and jump immediately to the row without scanning anything else. So here this time with the non-clustered index, the SQL did read 3 different index pages and finally the one data page in order to find the data. So if you compare to the clustered index, you can see that we have here one extra layer, one extra index page to be scanned in order to find the right place of the row. And this is how SQL creates the B-tree for the non-clustered index and how it scans it in order to find the information. Alright, so now when I think about the clustered index and the non-clustered index, I think about a book. You can think of the clustered index like the table of contents at the front of the table. So the table of contents gonna tells you where to find each chapter, and the chapters are exactly sorted like the table of contents. And this is exactly what the clustered index does. But now on the other hand, think about the non-clustered index as the index that you can find at the end of the book. The index of the book is a very detailed list of topics, terms, and keywords where it points exactly to the location where you can find it in the book. And the content and the topic of the book is not sorted like the index of the book. And this is exactly what the non-clustered index does. It is coexisting with the data. It is an extra list where it's going to point exactly where we can find the data inside our table. Alright, so now let's put those two indexes side by side to understand the differences between them. So the structure of the clustered index is a B-tree where it starts with the root node where we have an index page. This index page is pointing to the intermediate nodes where we have as well index pages. And those index pages are pointing to the actual data, to the data pages. So at the leaf level of the clustered index, we have the data pages, the actual data. What's special about the clustered index is that it physically sorts the data inside those pages. So everything here is physically rearranged and sorted. Now, if you are talking about the non-clustered index, we have as well a B-tree. So the same thing, at the root node, we have an index page pointing to an intermediate index page, but this time the intermediate nodes are pointing to another index page. They are not pointing like the clustered index to a data page, they are pointing to index page. So now if you check this structure, you can see that at the leaf level for the clustered index we have the actual data, the data pages, but on the other side at the leaf level for the non-clustered index we don't have the actual data, we have index pages. But those index pages are pointing to the actual data, to the data pages. But the big difference of that, the data pages are not part of the B-tree. The B-tree of the non-clustered index is just a separate structure that does not involve any data, so we have only index pages. And it just points to the data pages without changing anything physically with your data. But in reality, what happened is that you're gonna have those two types of indexes, the clustered and the non-clustered indexes, in one table. So what's gonna happen, the leaf level of the non-clustered index gonna be pointing to the data pages of the clustered index, because those index pages don't care whether those pages are sorted or not. It's just gonna go and point to the correct page and to the correct row. So that means we have now like two different B-tree structures that are pointing to the data. And here there is like one thing that you have to understand, that you can create only one clustered index on a table. And this rule really makes sense because you can store the data only in one way in SQL. And that of course makes sense because you can store the data physically only once. And that's why in SQL databases you are allowed to create only one clustered index, because physically the data can be sorted only in one way. But in the other hand, in the non-clustered index, you can create as many non-clustered index you need. So you can create 3, 4, and all of them are pointing to the same data pages. Because in the B tree of the non-clustered index, you don't store any data pages. We store only pointers to the data, and you could have like multiple pointers. So this is the most important and the main difference between those two indexes. Now, if you put it side by side, we have learned that the clustered index gonna go and physically sorts and stores the rows at the B tree. But the non-clustered index is gonna go and create a separate B structure with pointers to the actual data. And by the way, the clustered index, we call it the main index that we could use in each table. So the clustered index is the main one, the most important one that you can go and use in each table in your database. Now, as we learned, if we are talking about the number of indexes, you can create maximum one index for each table. But for the non-clustered index, there is no limitations. You can go and create multiple indexes for each table. And now, if you go and compare them about the read performance, how fast we can get data using clustered index? Well, it is faster than the non-clustered index. And that's because in the non-clustered index, we have this extra layer at the leaf node from the B tree. And because of this having extra layer, that means SQL has to do extra job in order to find the data. That's why clustered index is faster than the non-clustered index. But now, in the other hand, if we are talking about the write performance, how fast we can insert data to the tables? Well, writing data to a table with a clustered index is slower than the non-clustered index. And that's because as you are inserting data to the table, SQL has always to check the data pages. Is everything sorted correctly? And if not, SQL has to go and start physically sorting the data again in order to have the correct order. So there is a lot of stress in order to sort the data with the clustered index. But in the other hand, in the non-clustered index, we don't have this. So the physical data gonna stay as it is. We are just creating nice new pointers. So if you are writing to a table where you have a clustered index, it's gonna be slower than writing to a table where you have non-clustered index. And of course, the fastest way to write data to a table is to not have indexes at all, so a heap structure. So SQL just go and start inserting data inside those data pages without creating any extra structures. So as you can see, it's like always a trade-off. You can read fast, but you're gonna write slower. So you cannot have like everything. Now, if we are talking about the storage efficiency, the clustered index is gonna be better with the storage than the non-clustered index, and that's because of the same reason. With the non-structured index, we have this extra layer of index pages, and index pages needed storage, and that's why they're gonna waste more storage than the clustered index. Now, if you're talking about the use cases, when to use clustered index? Well, if you have like a column, this column has to have a few criteria in order to be a good candidate for the clustered index. First, it's gonna be good if the values inside the columns are unique. And second, and it is way more important than that, the values of this column should not change a lot. Because if this column having a lot of update operators and the data is keep changing, that means each time SQL gonna go and start sorting the data again, left and right. So having a column that is frequently changing, it's not good for clustered index. And that's why the primary keys of tables are a perfect candidate, because first, they are unique, and second, we will never go and update a primary key value. We always append a new primary key value. And that's why primary keys are perfect for clustered index. And one more thing where I go and use clustered index is that to optimize the performance of a range query. If you are querying the data between one value and another one, clustered index works really well. Now, in the other hand, if we are talking about the non-clustered index, we could use it on columns that are used in the search conditions, or if you are joining tables without using the primary keys, then you can go and apply the non-clustered index in order to have faster joins, or you can go and use it to optimize the performance if you are searching for an an exact value, exact match. So those are the main and important differences between the clustered and the non-clustered indexes. Alright, so now before we go to SQL and start practicing, I would like to show you the syntax of the index. So it's very simple. It starts with create, and then we can define whether it is clustered or non-clustered, and then the keyword index. But this section is optional, so if you don't define anything, the default can be the non-clustered. So if you say create index, the SQL server gonna go and create non-clustered index. Then after that, we have to go and define the name of the index, and then we have to tell SQL which table we have to create the index in on table name, and then we can go and define one column or multiple columns for the index, and we call an index with multiple columns as composite index. So for example, we can go and create a clustered index using this command, create clustered index, the index name, and then we specify the table and the ID. So we are saying create clustered index based on this column, the ID from the table customers. And if you want to create a non-clustered index, you say create non-clustered index, and the same thing. So far we are using one column in the index, but we can go and create a composite index with multiple columns, like the following example. So we can say create an index, and as you can see, we skipped here defining the type, and that's because the default gonna be non-clustered index. And now here we are specifying two columns, the last name and the first name. And as you can see, we're specifying as well for SQL how to sort the data. So we are saying last name should be sorted inside the data page, ascending, lowest to the highest, but the first name should be the way around, from the highest to the lowest. So you can control how the data can be sorted physically in the data page. So as you can see, it is very simple. This is the syntax for creating index in SQL. Alright, so back to SQL, and the first question is, where do we find indexes in the database? Well, you can go and explore it if you go to the Object Explorer over here and check any tables from our sales DB, for example, the customers. And here you have a folder called indexes. So if you expand it, you will find here an index. I didn't create any of those indexes in the database, but in SQL Server, if you define any of the columns as a primary key, the SQL Server gonna go by default creating a clustered index for the primary key, because it makes always sense to create a clustered index on the primary key. So this one is created as a default, and as you can see at the start, we have like a key, primary key customer, and then it is clustered. Now I would like to start from the scratch. That's why I would like to go and create a new table without any indexes. So what we're gonna do, we're gonna go and load the table customers into a new table. So how we can do that? We're gonna go and say select star from sales customers, and before the from, we're gonna say into a new table. So it's gonna be TB customers. So like this. Let's go and execute it. So now if you go to the left side and refresh the tables, you can find we have now a new table called DB customers. Now let's go and check whether we have any indexes inside it. So indexes, it is empty. So we don't have anything, no clustered index or anything else. And this table has the structure of heap structure. So the data are inserted there randomly, it is not sorted. And if I go over here and, for example, let's say I'm gonna select from this new table where customer ID equal 1, and I execute it, the SQL Server did a full scan on the table in order to find this customer ID. So our new table DB customers is a heap cluster. But let's go and change that. What we're gonna do, we're gonna go and create a new clustered index. So we're gonna say create clustered index, and then we're going to go and give it a name for the index. We usually follow the following index, so we have index as prefix, and then after that we specify the table name, so DB customers, and then the key for the index, so the column that you are using in order to index the table. This is important to stick with the same naming convention for the index name, because later as you are monitoring your indexes, it's going to be really easy to understand, okay, this index is for the table DB customers, and we are using the customer ID to index. So now after that, we're going to go specify on which table we are doing the index. So on sales DB customers, and then we're going to specify the column name. So we are saying build for me a clustered index based on the customer ID. So now let's go and execute it. So as you can see, it's very fast because we have only 5 rows. So the database just switched all the data pages very fast. Now let's go and check our new index. So let's go and refresh and let's go inside it. And now we can see that we have our new index, clustered index based on the customer ID. Now, as we learned, we cannot create multiple clustered index, but let's go and test that. So I will just take the whole thing. And let's say I would like to create a clustered index based on the first name as well here. So let's go and execute it. So as you can see, SQL saying you cannot create more than one clustered index on this table. That means we can create only one clustered index. And let's say that after you created the index, you chose the wrong column and you would like to change it to the first name. So what we're gonna do, we have to go and drop the index. So we say drop index, and then you need the index name. It was this one. And then you have to specify which table. So it's gonna be sales DB customers like this. So if I do it like this and let's go and refresh again, you can see that we don't have any indexes anymore and the table is backed as a heap structure. And now you can go and create the correct clustered index for this table. But to be honest, I'm gonna stick with the customer ID, so I will not create a clustered index on the first name, because the first name of course is not unique. You can have like maybe multiple customers having the same name, and as well updates could happen on the first name, and that's gonna be very expensive. So that means I'm gonna stick with my index on the customer ID. Let's go and execute it. And now I have again my index on my table. Now let's say that I have the following select statements from our tables. So customers, and I'm searching for the last name, where let's say we are searching for Brown. So let's go and execute it. So let's say that we are getting more and more customers and our table is getting bigger, and I frequently use this query. So I'm searching for specific customers using the last name. So what we can do, we can go and create a non-clustered index for the last name in order to improve the performance of this query. So let's go and create that. So we're gonna say create non-clustered index. And now we're going to give it the name using the naming convention. So DB customers, and we're going to use the last name for this index. So on sales DB customers, and we will use the column last name for the index. So let's go and execute it. And now if you go to our indexes and refresh, we will find our new index over here. And as you can see, it says it is non-clustered and as well non-unique. We will talk about the uniqueness later. So as you can see, it's very easy. We have just created a non-clustered index on the last name. And now as we learned, we can go and create multiple non-clustered index on the same table. Let's say, for example, now our query looks like this. We are searching for the first name using, for example, the value Anna. And now this query happens a lot and maybe slow, so we can go and create a new non-clustered index. So let me just have it like this. And for the non-clustered index, you don't have to specify always like non-clustered index. As default, it's going to be non-clustered, so we can skip that. And here, let's call it first name. And the column that we are using is the first name. So let's go and create this index. And now let's go and refresh our indexes. And as you can see, SQL did create a non-clustered index for the first name. So if you don't specify the type of the index, it's going to be, as a default, non-clustered index. Alright, so now let's talk about the composite index. It is an index that has multiple columns inside the same index. So far, we have used only one column in the index, but we can go and specify multiple columns. And that's because sometimes our where conditions are complicated and based on multiple columns. So for example, let's say that we are searching for country equal to USA, and at the same time we are saying the score should be higher than 500. So that means in this condition we are using two columns and we would like to speed up this query. So how are we gonna do it? So we're gonna go and create, let's say, an index and give it the name DB customers, and let's say country score on sales DB customers. And now it is very important to do the following thing. Now we have to go and define a list of columns that we want to be included in this index. And it is very crucial and important that you get the same order as your query. So your query starts with the country and then the score. You have to do it the same thing in the index. So the first column, it's going to be the country and then the score. So it must be the same order as your query. So let's go and create this index. And if you go to the indexes over here, you can see that we have created our new index. So now once you create such an index and your table gonna be like always updating this index, you have to be committed and responsible. So in your queries, if you want to filter the data using country and score, always start with the country, then the score, in order to be able to use the index optimizer. So if you do it like this, the index is gonna be working. But if you go and query the way around, so you start with the score and then the country, the SQL will not be using your index. So either you adjust your queries or you have to go and recreate the index based on this switch. So be very careful with the composite indexes. The order is very crucial. So you're gonna have it exactly like the query. And now you might say, you know what, now we have like a nice index for those two columns. What can happen if I go and use in my query only one of them, like for example the country? So now the question is, if I go and execute this query, is the SQL is using this index even though that I don't have the score? Well, yes, because it follows the leftmost prefix rule. So what this means, SQL can use the index if you are using always the left columns. So here in our index, country is on the left. That's why it is working over here. But if you go and skip the left column, it will not work. So if you go over here, for example, and say, let's go and select only the score, and it is like higher than 500, what we have done, we have skipped the country in this query, and that's why it will not be working. So as long as you are including the left columns, it will work, even though it is only one column. So in this scenario, the first query gonna use the index, the second one will not be using it. So now let me give you a very simple example in order to understand how this works. So let's say that we have an index using 4 columns, A, B, C, D. Now in your query, if you go and target the column A, the index is going to be used. Now the same thing going to happen if you go and use A and B. So if you are using those 2 columns, you will be using the index. So those are where the index will be used. So now let's have the scenarios where the index wants be used. So for example, if you go and just jump immediately to the column B, so you are not using the left column, the A, that's why you will not be using the index. And as well in your query, if you are using A and you are skipping the B, so you have A and then C, you will not be using the index. So you have always to use the left columns. So here, if you are using A, B, C, you will be using the index. And let's say here you are using A, B, and then you jump and skip to the D, you will not be using the index. So this is what we mean with the leftmost prefix rule by using the composite index. So if you are using multiple columns inside one index, be careful with the order of the columns that you are defining. Alright, so that's all for this category, clustered and non-clustered index. Now we're gonna move to the second category, where we talk about the indexes by the storage, the row store and the column store. If you like this video and you want me to create more content like this, I'm gonna really appreciate it if you support the channel by subscribing, liking, sharing, commenting. All those stuff gonna help the channel with the YouTube algorithm, and as well my content gonna reach the others. So thank you so much for watching, and I will see you in the next tutorial.